Yes.
Yes,
Oh, good.
I just
So
started.
I I go free. Good. Good afternoon to everybody. So we are here again. Today we shall take a small step forward to our final target, which is to understand something about RSA, the basic of cryptography. And we need some devices more. Last time we we talked about a set of numbers, natural numbers, integer numbers, rational numbers. Actually, we stopped with the rational numbers. And just to recap a little bit, you can enlarge the set of natural numbers by taking an appropriate uh, equivalent relation over the square of the natural numbers. You could do in principle the same thing from the rational number, from the integer numbers to the rational one by taking an appropriate equivalence relation on the square of z, the integer numbers. You can do the same thing going from the rational to the reals. However, this time, this is the most difficult. Um, this is most difficult equivalent relation to define because it involves notions that are too advanced. And surprisingly, it is easier to go from the square of the real numbers to the complex number than not to the square to the real numbers. However, this is just for your information, for completeness. Today's receipt, what we are going to talk about is divisibility, Euclidean division, what is known as the greatest common divisor, and hopefully, but I don't think so, prime numbers already this night, but it's very unlikely. I think we have a lot to do still. So let us start. Let me give a few names, a few definitions, so that we can go fast. Pick to. So let's start. Maybe I need this. Pick to integer AB as you like. So you can always say that you can always ask this question, and in the affirmative, you give a definition. Does A divides B? What does it mean? When A divides B, and you denote this by writing in between a vertical bar, this means A divides B, whenever there exists an integer C in Z such that B is equal to C times A. This this is equivalently stated as saying that B is a multiple of A, of course. So, for instance, 2 divides 4, and 4 is a multiple of 2, clearly. This is an easy definition. So we already know this definition, probably from the very basic school. But the question is every integer B a multiple of some integer A? This is the question. Of course not. Clearly not. For instance, 2 does not divide 3. However, we can do something. We have a very extremely powerful device, namely Euclidean division, which can be stated in the following way. For every pair of integer a and b in Z, there exists a unique integer m, which is in a sense, in exactly, not in a sense, exactly the closest lower bound to b from below. This means this is what lower bound means. An approximation from below, such that m is a multiple of a. So if you fix b and a, you can always find a multiple of a, which is as close as possible to b from below. Which, what does it mean? As close as possible. It means that any other multiple of a, other multiple of a, which is a lower bound of b, which is not larger than b, is not larger than m. This is closest. And the error we get by approximating b with a multiple, with this multiple of a, is always not greater than a, smaller than a. So this, you can think this as the arrow in curve when we approximate, no, this is not prime, this is m, sorry. This is the right one, the closest one. You can always think this as the error you incur when you approximate from below by a multiple of a. And this is the guarantee. You cannot go wrong by more than a. So this is somehow a perverse way to present Euclidean division, which is otherwise very well known, and whose formal statement is for each a and b in Z. So you pick any two integers, no matter what is their sign, no matter if they are zero or not, they always exist, and they are uniquely determined by a and b, two integers q and r, such that b has this following representation. You can always write b as q times a plus r. So this is the m above, the multiple above, the closest multiple above. And of course, r, if you think r as the approximation error, is always non-negative, but is smaller than a. This is very, very important. Now, despite its simplicity, this is a very deep fact in arithmetic, and it follows from Peano axioms, because the unicity of Q and R are consequence of the well-ordering principle. I mentioned it last time. It is equivalent to mathematical induction, but thanks to that principle, we can state the Euclidean division. Now, just to be sure that everything is clear, let us do some examples, because it is quite different from the usual division we know, which is more difficult somehow within the rational, because we have a constraint, and the constraint is that the approximation error, the remainder R, oh, sorry, maybe I forget to recall that Q is called the quotient, and R is called the remainder. So we can think of this reminder of the approximation error when we try to approximate B by a multiple of A from below. And we have these constraints. The reminder cannot be negative. It cannot be larger than or equal to A. This makes the difference because, look, 15 is, of course, 3 times 4 plus 3. This is the reminder. But just look at 15, so at the division of 15 by minus 4 rather than the division of 15 by 4. On dividing 15 by minus 4, you get a quotient of minus 3. Minus 3 plus minus 4 is 12. And the remainder is 3. So far, so good. But here is the difference. Suppose you want to divide minus 15 by 4. Oh, now you see that you have to put here minus 4 and add 1. And this is different in these two cases as really different. This does not happen within the rational numbers because minus A over B is the same thing as minus A over B. Here it is different. It's not the same. This is because we are forcing the reminder to be non-negative and strictly smaller than A. So this is Euclidean division, and as I said, this is far from trivial, and it requires the well-ordered principle to work. And we are grateful to Peano, who solved who put the axioms and solved this problem. And now we are free to go without asking anything more than what we defined. For instance, let us put some very, very easy question. The first question is, yes, we have a definition. Let us check how it works in, for instance, in special cases like the one that I listed here. Does 0 divides B? I don't know. Let me check. Can I find a multiple? Let us try. I check. Can I represent B as a multiple of 0? No, clearly not, unless B is equal to 0. If B is equal to 0, then this is true. 0 is equal to 0 times 0 plus 0. This is Q, this is R, it is 1. So we learned that 0 divides B if and only if B is equal to 0. Now, does B divides 0? Let us check. 0 Q times B plus R. Can I satisfy these equations? And if I can, provided that R is less than B, I can conclude, sorry. This is, sorry, it's not the Euclidean division, this one. Sorry for this. The reminder does doesn't matter. It does not sense in this. Sorry. Let me start again. Oh, yes, of course. What we have said so far is true. It's more generally true, but has nothing to do with the question I put. So the question is there, can I write B as a multiple of 0? No, unless B is not equal to, unless B is not equal to 0. In this case, 0 is equal to 0 times 0, and it is indeed a multiple. 0, it is a multiple of 0 indeed. So the other question is B a multiple of 0? Yes, of course it is, because 0 is always equals to 0 times B for every integer B. Is minus B a multiple of B, and conversely B a multiple of minus B? Yes, of course, just take Q minus 1 in both cases. Is it true that 1 divides B? Yes, of course, for every B, because B is always B 1 times B. And the converse is also true. What does it happen when B divides 1? Then B is necessarily plus minus 1. There are no other possibilities. I invite you to check these, which is this is an important, it's trivial but important fact. You have to convince that this is true. Oh, sorry. To convince yourself that this is true. So B is equals to plus minus 1 whenever B divides 1. And of course, think of the Euclidean division, which can be applied in this case. Now, we have seen these few facts about special cases, which are actually the hardest ones when one introduces some definition, some notion. You have to check if your notion is well defined, and to check whether it is well defined, you have to stress it in the special cases. Yes, the special cases are not in the mainstream of our imagination, so we sometimes, usually, find the special cases the hardest one to digest. Now, let us give some more properties of this relation. Let us see what can we do with this notion of divisibility. So suppose, for instance, for the moment that A divides B and A divides C. So in this case, we say that A is a common divisor of B and C. This is a very important, it is seemingly trivial, and of course it is, but it's very, very important. So if A is a common divisor of B and C, then A divides any expression of the form S times B plus T times C, whichever S, T, R in Z. This expression is called as a name. I don't want to insist, but it is good to know. The name of this expression is an integer linear combination of B and C. The coefficient of the linear combination, integer linear combination, are of course the integer numbers and are S and P. So in words, you can say whenever A is a common divisor of B and C, then A divides any integer linear combination of B and C. Allora, let us try to prove this easy statement. Assume first that A divides both B and C, and complete the proof by yourself. I do the other direction, which is easier. So suppose that A divides a particular linear combination, every linear combination of integer linear combination of B and C, but if A divides any integer linear combination of B and C, it of course divides particular linear combination and pick two particular linear combinations. One is obtained by picking S equal to 1 and T equal to 0, and you get that A divides B, and the other one is picking S equal to 0 and T equals to 1, and you get that A divides C. And this is and this is an error. There is a right difference between error, mistakes, and also typo. I would say that this is a typo. It's less dramatic somehow. So I don't know if this is clear. We want to prove that any time that A is a common divisor of B and C, then A divides any linear combination of B and C, and conversely, what I proved is that whenever A divides any linear combination of B and C, necessarily A divides B and A divides C. Therefore, you can say that whenever A divides any linear combination of B and C, A is a common divisor of B and C. And you can take this, this statement can be taken as a, this is not the way we will follow, but you can take this statement as the definition of common divisor. A common divisor is any number which divides any linear combination. A common divisor of B and C is any number which divides any linear combination of B and C. Now, let me give you the, for the moment, for the time being, this last definition. And then we start to play with an object we saw last time. So these strange sets of the form A times Z. But before doing that, let me give you this definition. So greatest common divisor. So we know what is a common divisor. A common divisor of A, B is any number C which divides both A and B. So let me call it D, just to be more mnemonic. This is a common divisor. The greatest common divisor is the largest integer with this property. So which means what I wrote here. The first row says, sorry, sorry guys. The first row says that D is a common divisor. The second row, this one, say that it is the largest common divisor, because let us read the second row. It says that if D prime divides A and divides B, divides both, it is of course a common divisor of A and B, and it is a divisor of D. That's why D is the largest common divisor. So let us do some practice with these concepts, and let us recall what we mentioned last time. So you hopefully you remember this set of this form AZ. Z is the set of integer number, a set of integers. So which is the definition of a Z? A is of course an integer, is just a set of the form. So I would say I would like that you in your mind says what is AZ after the terminology we introduced today. Pause a little bit and try to express in your mind what is AZ. A little bit is elapsed, so I can answer. And so AZ is simply the set of multiple of A. And so this is a mnemonic and elegant, as we will see, way to denote the set of multiple of A. Good. For instance, I wrote down a couple of examples. So pick 3Z. 3Z is the set of multiple of 3, so minus 12, minus 12, minus 9, minus 6, minus 3, 0. Of course, 0, we saw we saw that is always a multiple of any natural number, integer number, then 3, 6, 9, 12. Pick 6Z, that minus 12, minus 6, 0, 6, 12, and so on and so forth. Just let me drive your attention to these two sets. So, yeah, 12 is here, 12 is here, 6 is here, 6 is here, 6, minus 6, minus 12, 6 is here, 6 is here, 12 is here, 12 is here. So, and it's also clear that 3 divides 6, that 6 is a multiple of 3. So which is the larger of the two sets? 3Z or 6Z? Well, the larger one is 3Z. And we have this inclusion. Do you see why? But the reason is quite straightforward, because every multiple of 6 is also a multiple of 3, of course. And you are saying exactly this, that if A divides B and B divides C, then A divides C. That's why. Yes. This is quite nice, because it's suggesting that these sets so far already have some structure. For instance, they reverse divisibility in the following sense. If A divides B, AZ is a superset of BZ. We can do something more with these sets. We can complicate things, but we complicate things with the target in mind, because we want to do algebra on these sets. So we have seen AZ. Why not AZ plus B, which is a possible meaning of this set? A natural one is an AN is the set of multiple of n displaced by B. So you pick. How do you construct this set? You pick every multiple of A and you add B and put it in the other set, AZ plus B. This is just a simple construction. So, for instance, what is 3Z plus 1? It is simply 1 plus, sorry, I inverted the order, but due to commutativity, thanks to commutativity, I don't care about that. So, for instance, minus dot minus 2 1 4 7 dot. And you can do the same with, for instance, 5Z plus 3. And there are probably two very nice examples that you already know very well, and we mentioned last time. 2Z, this is 2 actually, which is the set of multiple of 2. This set has a name, a very a celebrated name. It is the set of even numbers. Also. And you also know this set, which is simply the set, as you know, of odd numbers. So last time we start to play with these two sets. My aim last time was to introduce the equivalence relations for an example, a very instructive, constructive example like this one. But actually, actually, I wanted to speak about something more difficult, so not so much, but a little bit more. And I wanted to speak about the set of multiple of three and the set of multiple of three displays and the set of multiple of three displaced by two and the set of multiple of three displaced by three. And after a while, I realized, and you realized with me, that probably these sets are too much. We don't need all these sets. Let us start with five. So, what is my claim? I wrote it here somewhere. Here. I claim that just these three sets, 3z, 1 plus 3z, 2 plus 3z, have a repartition of z. What does it mean, a partition? It means that whatever integer n you pick, this integer is exact in at least one, in exactly one of these three sets. So this is clear. If n is a multiple of 3, it is clear that it belongs, first of all, these three sets are disjoint. They have no common elements. I think you can see this. Anyway, of course, if you pick a multiple of 3 and add 1, you get a different number. So there is no number which is at the same time a multiple of 3 and a multiple of 3 plus 1, either 0, of not even 0. And the same is true for 2, and the same is true for 1 plus 3z and 2 plus 3z. So these three sets are disjoint. They have no common elements. But we are saying much more. We are saying that altogether, these three disjoint sets cover, exhaust the whole set of whole numbers, of integer numbers. Why this is true? Of course, if n is a multiple of z of 3, it is of course in 3z, and we are done. If I pick a number and differ by a multiple of 3 by 1, it is of course in 1 plus 3z. So for instance, if I pick 4, it is 3 plus 1, 3 times 1 plus 1, and so it belongs by definition to the set of multiple of 3 displaced by 1. These sets have a very special name. Let me recall for later purposes, or just for completeness, or just because it's nice to know. They are called cosets. Cosets. In this a terminology which comes from group theory. So any one of these is a coset. So 4 belongs to the cosets 3z plus 1. It is called also lateral class. If you think of straight lines in the Euclidean plane, you see what are the cosets. The cosets are every coset is a straight line which is parallel to a given straight line. And the role of these sets of the cosets is played by just one straight line. So in this case, this coset contains just one straight line. However, if you enlarge the definition, if you think more generally, and so I don't want to lose time in. Yes, you can identify any cosets by a particular direction in the Euclidean plane. No, it's too difficult. We don't need this. This is not too intuitive. So let's go. These are called cosets. So let us return to 4. 4 is in the coset 3z plus 1. Good. And 5? 5 is in the coset of 3z plus 2. And 6? Oh, 6 is easy. It is in 3z. And 7? And 7 can be written as 3 plus 3 plus 1, 2 times 3 plus 1. Oh, this is a multiple of 3, and this is 1. So this belongs to 3z plus 1. And 8, now you should have understood what I mean. It is 2 times 3 plus 2, or again 3z plus 2. And 27, 27, to which coset belongs 27? I don't know. 27 seems to be 3 times 9, so it belongs to 3z. And 28, 28 seems to be 3 times 9 plus 1. It belongs to 3z plus 1. So, to which coset n belongs to? Sorry. Plus r. What is r? Is just. So n belongs to the coset 3 times z plus r if and only if r is the remainder of the Euclidean division of n by 3. So we know that the remainder of the Euclidean, do you understand that? We did several examples to explain why this is true, because of course n can be always written as a multiple of 3 plus r, always. But this means that this is a multiple of z, a multiple of 3, and this is R. So we know that R is always smaller, strictly smaller, or not larger than Q minus 3 minus 1. So R is always non-negative and not larger than 1, which means that R can be only 0, 1, or 2. So we proved that 3 seed union, 3 seed plus 1 union, 3 seed plus 2, this is Z, which is the meaning of this picture here. It's, which give you a pictorial flavor of what a partition is. But this is quite general. You can do this partition and you can recover the same result by choosing any integer in place of 3. This is called the modulus. Replacing 3 by any integer number, for instance, fix an integer number m now. M can be, yes, a restriction. We have a restriction. We assume the m is positive natural number. But if you pick any positive natural number, then you can always write Z as mz union mz plus 1 union, which is the last one, is m minus 1. Notice that implicitly today we already define some operation in, of course, this is in a tacit way, but tacitly, but we did it. For instance, we did, without saying it explicitly, that A plus BZ plus, these are still not, these are yet no meaning, but we did it. And we will do it formally next time. But you can guess that this is true. You can, rather than guess, you can agree that this is, no, sorry. This is C. That this is quite natural, and you can also give a meaning to this operation. However, this is not the this is not the content of this lecture. We have just to digest what are these strange symbols here, and to get acquainted with the way they cooperate in Z with this partition here. So this is our aim for today. Now we have some familiarity with this set and also with these cosets. So and also with the sum of two cosets. Let me explain this a bit better. So far we have seen AZ, we have seen the cosets, A plus B, AZ plus B, but we can do the same with some of, say, cosets in this form. So far, this is not an operation. This is not an operation. It's just a mnemonic symbol, which means the set consisting of all the sum of multiples of A and multiples of B with coefficients, with integer coefficients. So we have already given a name to these objects, to the elements of this strange sum AZ plus BZ. Which is the name of these elements? It is linear. It is the set of linear integer combination of A and B. And so we already know, and it's easy to see that this set, so let me put you this question, which is the relation between this set and this set, this, where D is AB, namely the greatest common divisor of A and B. We know that if we know that if you have a common divisor of A and B, then this common divisor divides every element of the special set. We already saw this, no? If B is a common divisor of I and B, then B divides any integer linear combination of A, and B. Please think sometime on this relation, and in the meantime, I will introduce another small device just to visualize the relation between these sets. And there is a nice way to represent the relation, the inclusion relation in general, the order relation. Yes, I think I spent a few words on order relation. The equivalent relation, you know, are the relations which are reflexive, symmetric, and transitive. Order relation are those relations which are symmetric, reflexive, transitive, and anti-symmetric. The inclusion relation between sets, being a subset of another set, is a relation which is transitive, of course, reflexive, of course, because you consider always a set a proper subset of itself, and anti-symmetric because if A is a subset of B and B is a subset of A, there are no other possibilities to be the same set. So pick, for instance, all the subsets of the set 1, 2, 3. 1, 2, 3 is, of course, a non-proper subset of itself. So you put in the set of all subsets of 1, 2, 3, but 1, 2 is a proper subset, 1, 3 is a proper subset, so 2, 3 the same, and so on and so forth. And the empty set is still a subset, is again a subset of 1, 2, 3. It is a non-proper subset of 1, 2, 3. But once you have all these subsets, you can order them by inclusion. So you put the largest one on top, and you put the other sets, all the other sets below, but beware. This is the cover relation. I don't want to introduce this. You put a subset just write down the 1, 2, 3. If it is a subset, but is somehow there are no other subsets in between. So you see 1, 2, 3, 1, 2, there are no intermediate subset between 1, 2, and 1, 2, 3. So this is the cover relation. So once you do that for every of the subsets, you get a picture like this, which is called the Haas diagram of the order. So we know already something. We want to use this Haas diagram. We want to use this Haas diagram to depict the various relations which subsist among the subsets of the cosets of Z with respect to a given modulo, or the sum of the coset with respect to two given modulus. I'm just talking about these strange sets here with when the modulo is 3, or this set here when the modulus is M, or even a set like this, which is the set of linear integer combination of 2 and 3. So let us start. Pick two numbers, A and B, and consider these cosets. Then consider these cosets. And consider this coset. This other set is not necessarily a coset. So let us try to draw a small Haas diagram between these 4 sets. So what is this one? Is the set of linear integer combination of A and B. The other two are AZ and BZ, and their intersection. Good. Of course, so what is this set? The intersection between the set of multiple of A and the set of multiple of B. of course, is the set of common multiples of A and B. So if M belongs to this set, it means that M is a multiple of A and M is a multiple of B at the same time. So is a common multiple. Of course, every common multiple of A and B is a multiple of A. So this set AZ is at least as large as this set. And so mm, provisionally, but not, I couldn't do that because I didn't yet prove that that this is a correlation, there is nothing between. However, just to forget about for a while, forget about the Haas diagram. This is just a way to say that the set above is larger than the set below and contains the set below as a subset. And the same is true for BZ, because of course, every common multiple of A and B is a multiple of B. So this set is contained in BZ. Why this is true? Why is it true that the set of linear integer combination of A and B contains both AZ and BZ, called the addenda of, so called the cosets, these two cosets. Why this is true? Yes, because it is true that AZ, the set of multiple of Z, is a linear combination of A, is a subset of the set of the linear combination of A and B? Of course, because A can be written, always can be written as 1 times A plus 0 times B. So this is a special linear combination, and every multiple of A and A can therefore be written always as n times A plus 0 times B. This is another special combination. Not every integer linear combination has this form, but this is an integer linear combination. So every multiple of A is a special linear combination of A and B. So it is true that AZ is a subset of AZ plus BZ. And the same is true for BZ. Oh, but both these two sets are a bit strange. And now we pause just for a few minutes. We take a, we take a little break, and then when we come back, I will try to convince you that this set is precisely the set of multiples of what? This is what we will prove in the next hour, that is that AZ plus BZ is precisely DZ, where D is the greatest common divisor of A. And so let us pause for say 3-4 minutes, 5 maybe, and see you in 5 minutes. See you. So I'm back. I hope you're still alive. And so let's so it is. Oh, good. So I hope you see again. And we left with small diagram with the promise to prove this claim, which by no means trivial. And so just me say a few more words about this relation. We know that any common divisor of a every common divisor of A and B divides any linear combination of A and B. Any linear combination and every linear combination. So in the just rewriting the diagram, you can say that. And also, as we saw, that one and that one. So every common divisor of A and B is above the set of linear combination of A and B. It's because we have just proved. We have seen that if D is a common divisor, D divides any linear combination. So every linear combination of A and B is a multiple of a common divisor of A and B. We proved at the very beginning this fact. So this diagram must apply. But are we sure that there is nothing in between the set of linear combination and AZ and BZ? We are sure there is nothing in between if we prove, and only if we prove, that the set of linear combination is exactly the set of multiples of the greatest common divisor. And so this is what we want to do. Is not trivial at all, actually. And so I just to expose you to a way of reasoning in algebra, and you will see that abstracting a little bit, things becomes easier. So what is AZ plus BZ? Is the set we see, it is the set of linear combination of A. Which property does this set have? Well, call it, provisionally call it S. So one obvious fact is that 0 is in S. Why 0 is in S? Because you can pick S equal to T equal to 0. This is a special linear combination because These are special coefficients of the linear combination. And if you put 0 here and 0 here, you get 0. So 0 is the result of the special linear combination, and it is in S. Is it true that if n belongs to S, then also minus n belongs to S? I don't know, let us check. If n is a linear combination of A and B, then minus n is a linear combination, a special linear combination of A and B. And this is true. Actually, this is enough. This is already, if one can see that, but we already already saw that the multiple of A are in the set of linear combination, the multiple of B are in the set of R in S, so that the multiple of any element of S is in S. So S is closed, which means S is closed with respect to taking the negative, the opposite, and taking multiple. Closed means that closed with respect to an operation means that every time you apply this operation, you are still in the set. To an element of the set, you are still in the set. Now, this just to be self-contained, but we are talking about a precise structure, and what we will basically show is that S is a subgroup of integer, and as such, it has a special form, and the special form, it is a multiple of some well-chosen integer in the set. I didn't say anything so far, but now it is to prove. So recall, S enjoys this property, 0 is in S. So the set of linear combination of A and B have the property that 0 is in the set. Whenever an element is in the set, is additive inverse is in the set, and also it is close with respect to taking multiples, and this gives the structure. But we don't need the structure. Now, here we we resort to Peano, invoke Peano, we thank Peano, because, look, S is clearly non-empty because A and B are not both 0. No, we don't need this. S is clearly non-empty by definition. There is at least one element, for instance, A or B. So S is clearly non-empty, and we can intersect S with the set of natural numbers except 0. So we pick our set of integer linear combination of A and B, and among this linear integer combination of A and B, we throw out those whose result is negative, or 0. And we retain whatever is left. Is this set empty? No, it's not. Why it is not? Because of this property. Because of this property. Oh, sorry. Oh, sorry. This property guarantees that S is not empty because pick an element. There is at least one element, say A. If A is positive, A is an integer linear combination. If it is positive, it belongs to this intersection. If it is negative, well, is negative is positive, and it is still in S. It is still a linear integer combination. So this set is non-empty. So we can write this. We can negate. And moreover, what is most important is that this set is non-empty subset of the set of natural numbers. Since it is a non-empty subset of the set of natural numbers, we can apply WOP, well-ordering principle. And the well-ordering principle says that each non-empty subset of the set of natural numbers has a smallest element, namely an element of you can order the set, totally order the set of natural number. Say that 0 is the smallest, 1 is the second smallest one, 2 is the second smallest, it is smallest one, and so on and so forth. You can totally order the set of natural numbers. What the principle says, yes, even if you pick a piece of the set of natural number, a subset of the set of natural number, you can always locate this smallest element. So you say, this is a triviality. Why do we need a principle for such an obvious thing? We need, I don't want to bore you with strange stories or matters related to the foundation of mathematics, but you need, trust me, it's not trivial to have this principle. Of course, you can do everything. You can do everything without axioms. You can also think that the line is flat, that P Greco is rational, whatever. You can think whatever you like. But if you do that, for instance, there is a special axiom which is called the axiom of choice. If you don't accept the axiom of choice, you have to accept that if you pick a sphere, a large ball, you can decompose this sphere, this ball, in several pieces, and you can recompose these pieces to get two different spheres of the same volume. So I don't know what is in the various tongues, the multiplication of bread and fishes in the Canaan weddings. But this is Banach Tarski paradox, and it is possible if you negate something basic like the axiom of choice. So you need the well-ordered principle to state things formally and consistently in mathematics. Otherwise, you cannot. However, we have this stupid thing, the well-ordered principle, which follows from the from Peano's axiom, and so this set, this intersection, has a smallest element. Call it, call the smallest element D. So we claim that every element in this set is a multiple of D. Clearly, it is true that this is a subset. We saw this. S is closed with respect to taking multiples. In particular, it is closed with respect to taking positive multiples. So this is true. The set of positive multiples of, in general, the set of multiples, even more is true. However, the set of positive multiples is clearly, is trivially a subset of the set of positive linear combination. But we want to prove that this is not a proper inclusion. These two sets are equals, and this is true because, because again, by the well-ordered principle, this time via the Euclidean division, because suppose for contradiction that there is an element n in S. Now I forget for a while this intersection. But suppose there is an element n in S which is not a multiple of D. So if it's not a multiple of D, the Euclidean division says that you can approximate n from below by a closest multiple. You can get as close as possible to n from below at the price of an error R. So you can write and just divide n by D, and you get by the Euclidean division this representation, but R, remember, don't forget, is smaller than D. But now we are done because R is n minus q times D. So R, what is R? Is a linear combination. So n is a linear combination is a linear combination of A and B. Why it is a linear combination? Because n is a linear combination. D divides every linear combination. So this is indeed a linear combination, but it's impossible because you would have found an element R which is in S but is smaller than the smallest element of S, which is a contradiction. So the only possibility is that if R is equal to 0 and n is a multiple of D. So what is this? What is the moral? That the smallest element in the set of linear integer combination of A and B is precisely the largest common divisor of A and B. And moreover, we proved much more. We proved that every subset S of Z, which is closed under taking the negative and contains 0, it is of the form, it is the set of multiples of some particular integer d, which is the smallest positive integer in the set. So this is actually a very, very, very strong result, because we know now very well these are called, I already say, these are called subgroups. So without without pretending to be formal or exhaustive, we proved essentially that any subgroup of integers of the group of integer numbers is of this form. Good. Now this is what we wanted to prove. And this fact is very, 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 very important, both theoretical and algorithmically, and now we will see why. Let's go to good. Now we know what is the greatest common divisor, and of course this is the definition, the standard definition, but we characterize the greatest common divisor of two integers a, b as the smallest positive linear integer combination of A and B. Now, these facts follow easily from the definition without resorting to the result we just proved. And of course, the greatest common divisor of A and 0 is modulus of A. Recall that, let me stress this fact here. Oh, that the greatest common divisor is a positive, is a positive number. So if A is a positive number, the greatest common divisor between A and 0 is A. If A is a negative number, then the greatest common divisor of A and 0 is minus A, which means modulus of A. Yes, so we know that. We saw that plus minus A divides A. This is by definition. A divides A, of course, the property of the divisibility is a reflexive relation, and when restricted to positive numbers, when restricted to natural numbers, it is also an order relation. But in general, it's not, because it is true that 2 divides minus 2, 2 minus 2 divides 2, but they are not equal. They are non. It lacks antisymmetry. However, if A divides B and B divides A, it is true within natural numbers that A it equals to B. So plus minus A divides A, and 0 divides everything. So the largest the largest divisor is precisely the positive between plus and minus A, namely the modulus of A. This is also easy, which is the largest common divisor between A and plus minus 1. It is 1, of course. And the same is true for A plus minus A. It is still modulo of A. Just check. These are trivialities, but this is strong. This is really very strong. Bezout identity. And this is so strong and so straightforward after we have proved the result about the structure of the greatest common divisor. It is just a special case of what we see. If D is, so look, it's very strong, but we know now it is a very trivial consequence of what we proved. If D is the greatest common divisor, maximum, largest, whatever you like, of A, B, then there exist two integer number ST such that you can write D as an integer linear combination of A and B. Of course. Clearly, this is true. Why is it true? Because B is, by what we proved, the smallest of such linear combination. Therefore, there exists one. Please note, however, that differently from what we said about Euclidean division, S and T are not uniquely determined. So, indeed, the Bezout identity asserts that there is at least one a linear combination, but there are actually infinitely many, because if S and T is SA plus TB is any such combination, sorry, so I'm talking about this. If D is any such a linear combination, so you just check the easy computation. If you subtract within the brackets n times B and add within the other brackets n times A, you get the same result, but with different coefficients. So you can make these arbitrarily small or arbitrarily large as you like, without changing the property. So it is not unique, but it doesn't matter. The important fact is that there exists one such a linear combination. It is really important, especially when D is equal to 1, that is when the largest common, the greatest common divisor between A and B is 1, and in this case, the number are said to be coprime. When the number are coprime, that is, they have no proper common divisor, since once divides everything, it is always a common divisor of every pair of integers. It is called a not proper divisor. A proper divisor is a divisor which is different from one. When A and B the only common divisor of A and B is the trivial one. We say that A and B are coprime. Then when A and B are coprime, Bezout identity gives us a way we will see, and you will implement this probably with Paolo Franciosa or Fabrizio D'Amore. You can compute the inverse of an element in a residue in say modulo and field with prime module, or even in another field in a ring when the module is not prime, but the element you are inverting is co-prime with the module. So this is really, really algorithmically important. And so Bezout identity defines D as a not uniquely determined linear combination of A and B. Good, but it defines D as a linear combination. We construct this linear combination, and if it happens that you can express one as a linear combination of A and B, you can be sure that A and B are coprime. So it's not true. This is a very interesting consequence. It's not trivially clear why this is true, but it follows by the construction. So if one is a linear integer combination, yes, you have to, there is a small proof here, but you should complete this proof by yourself because it is instructive and easy. However, there is, I will put this, this lecture on the on the material folder. I don't know if there is a folder in Classroom where I'm going to put this lecture. So try to prove it without any hint, without any suggestion. And so the existence of and the unicity, it follows by the well-ordering principle, and also its definition followed by the well-ordering principle of the greatest common divisor implies Bezout identity and therefore a way of inverting arithmetically elements in ring modulo n, at least when the element to be inverted and the modulus are coprime. We will see this from a theoretical point of view, and you will implement this from an algorithmic point of view. But also it implies Euclid's lemma. I want you to prove by yourself this lemma, which is very, very instructive, because what says what Euclid's lemma says? It says that if A divides the product of B and C, and A and C are coprime, the greatest common divisor is 1, then A must divide B. So, yes, some of you may know the fundamental theorem of arithmetic, and you know we will shortly see this theorem. But you know that every integer can be factorized into its prime factors, each one counted with its own multiplicity. So every integer up to the order of the factors can be written as a product of powers, possibly trivial powers, namely when with exponent 1 of a uniquely determined set, uniquely determined by A, of course, of prime numbers. So probably you know this. Of course, you can permute you can change the order. So the unicity of this representation is given up to the order of the factors. So you can see why Euclid's lemma is true, and I ask you to prove it using the definite Bezout identity. It is really one line of proof. You can try to prove. Of course, Euclid didn't know Bezout identity, and his reasoning was very different, and something like the one I am saying now. Pick a factorization of A into primes number, of B into primes factor, of C into primes factors. So of course, the product of B and C is the product of the factorization. Now, what does it mean that A and C are coprime? It means that they have no prime factors in common. So in this product, A cannot divide the prime factor of C because there is no common factor between A and C, but A divides B and C, so it must divide the prime factors of B. This is a way to see Euclid's lemma, but to prove this in this way requires the fundamental theorem of arithmetics. Indeed, on the contrary, it is just one line proof using Bezout identity. It's a trivial consequence of Bezout identity. Before closing, there is still too much left, but I want you to do some exercise with you and to leave you some other so that you can train with this notion and get familiar with this. So simple way of saying something about the greatest common divisor of two numbers, even general numbers, without doing calculation. So let us start with one of these. So for instance, I do this one, and I like to use this one, which is a generalization, and probably this one, which is easy, and probably this one, just to, and I leave you this one. I let you this one with this more arrow. No, also this one, which is easy, and this one. So let us start with this, which is the easiest one. We want to prove that for every integer number n, n times 4 plus 5 and 5 times n plus 6 are coprime. So their greatest common divisor is 1. So look, we are not saying that 9 and 11 are coprime. Yes, we are saying exactly this, but more general, we are saying that every pair of numbers of this form are coprime, which is actually strong. So how can you cope with an exercise like that? These are mostly always the same, but just to appreciate the powerfulness of the zoo identity, we solve some of this. So look, we are looking for the greatest common divisor of these two numbers. We know that if D is their common divisor, which of course seemingly depends on n, but the claim is that this is not dependent on n. However, let us go provisionally the n. We are trying to, if this is the greatest common divisor of these two numbers, then it must divide the two numbers and any of their linear integer combination. Pick a special linear combination. For instance, the linear combination 5 times plus 5 minus, let me write in this way, plus minus 4. So this is our A, this is our S, this is our T, minus 4 times the second number, which is our P. If you do the easy computation, you get 20 and minus 20 and simplify, their sum is 0, plus 25 minus 24. So this linear combination is 1. We are done because we have found a linear combination which is 1. This is a clearly stated remark. If you don't believe in the remark, you prove the statement trying to do that without looking at the solution. However, if you don't want, just look at the proof, and you see that whenever two number FB have a linear combination which equals one, then their greatest common divisor is 1. Therefore, the number are coprime, and this is true. Now, this is an easy exercise, and I ask you, I hope you will enjoy to try to solve a more challenging exercise, but it is essentially, this is another typo. This is, you have to put plus here. So this is A and this is B. You can solve this exercise exactly in the same way we solved this special numerical exercise. So let us look to another one. For instance, this one, the second one, AB and A plus B. So what is the exercise asking for? It says that the product, the greatest common divisor of A and B and A plus B divides the greatest common divisor on the a squared b squared. This seems to be more challenging. Let us do some. So we want to prove that the greatest common divisor between a squared b squared is a multiple of the greatest common divisor of a times b and a plus b. Just to simplify the notation, write this d and write this d prime. We have to prove that d divides d prime. So this is what we want to do. Of course. So what we know, d is a common divisor of a b and a plus b. So d divides a plus b, but then if d divides a plus b, it divides any linear combination of a plus b and ab. In particular, it divides any multiple of a plus b. And why not the multiple a times a plus b? So d divides, I choose as S A and T 0. This is a special linear combination, which is equal to. So we get that D divides A squared plus AB, and also we know that D divides AB because it is the common, because it is a common divisor of AB and AB, so it is a divisor of AB. But again, if D is a common divisor of two numbers, it divides any linear integer combination of that numbers, of those numbers. So why not this combination? This is the first number. This is our S. This is our T, which means that, which means that D divides A square. And exactly for the same reason, D divides B squared, which is the only difference, and you have to change the linear combination and putting sorry, which is the unique difference, and you have to choose rather than A for S, B for S, and you get B squared plus AB, and you repeat exactly the same argument to get the same conclusion. When you got this conclusion, you are done, because this is exactly what we want to prove. D divides, the grid divides any divisor of, in particular, the common divisor. Any common divisor, in particular, the greatest common divisor of A squared, B squared. So let us, all the other exercises are up to yourself. And so I wanted to say a little bit more, not too much more. You see, there is, there are few a few things left, but they are many more than I expected. However, so let us stop here. I hope you have enjoyed this lecture. As I understand that this is not too funny. However, I think it was more pleasant than the first one, and I hope and think and believe and guess then the third one will be more funny than this one, funnier than this one. Good. So see you next time. Good. See you. Ciao, ciao.
Bye bye.
Goodbye.
Bye.
Bye.
Goodbye.
Ciao.
Thank you for joining.
Good. Ciao, ciao.
Bye. Have a good night.
You too.